all that is external to the system is called as the surroundings or environment of that thermodynamic system. System boundary. The boundary is that which separates the thermodynamic system from its surroundings. The boundary may either be fixed or moving. The system and the surroundings together comprise a universe. Let us consider a real-life example of a microwave oven as a thermodynamic system. We see that the body of the microwave oven forms the boundary of the system, and all that is enclosed within the boundary forms the system. The external environment forms the surroundings of the system. Closed system. A system of fixed mass is called as a closed system. In a closed system, there is no mass transfer. In a closed system, there is energy transfer into or out of the system. As an example of a closed system, let us consider a steel vessel filled with hot water and covered with a lid. Since the vessel is covered with a lid, there is no mass transfer, but the temperature drops down after some time, so energy transfer does take place. Open system. In an open system, matter crosses the boundary of the system. In an open system, mass transfer happens across the boundaries. But energy transfer is optional. That is, energy may or may not be transferred. Example. To understand the open system, we will consider the same example of hot water kept in a steel vessel, but now without a lid. Now here we have heat energy crossing the boundary of the system to the surroundings through the walls of the steel vessel. The water evaporates in the form of steam, and so mass gets transferred from the system and surroundings. Therefore, in this case, we have transfer of mass and energy both. Isolated system. In an isolated system, there is no interaction between system and the surroundings. Hence, it has fixed mass and fixed energy. Observe the given schematic diagram. A real-life example of isolated system. A truly isolated system does not exist in reality. The universe is considered as the only real-world example of an isolated system. Some real-world situations can be approximately isolated systems. For instance, hot water stored in a thermos flask is an isolated system. In a thermos flask, matter can neither enter nor leave the system since the vessel is closed. In a thermos, heat energy does not radiate out of the system since the vessel is well insulated. So here we can see that neither mass nor energy is transferred from the system to the surroundings. So in this session we have studied thermodynamic system, surroundings and system boundaries. We also defined closed system, open system and isolated system.
So next is about thermodynamic equilibrium. Let me see what is thermodynamic equilibrium. Thermodynamics deals with equilibrium states. A system is said to be in thermodynamic equilibrium if it maintains thermal, mechanical, phase and chemical equilibrium. Thermal equilibrium means what? It means that temperature is the same throughout the system. In all system, the same temperature is there at every point. It means that there is a thermal equilibrium. Then mechanical equilibrium means the pressure is the same throughout the system. No pressure variation is there throughout the system. Then it is called as the system is in mechanical equilibrium. Then phase equilibrium means no phase change process in the system, means throughout the system single phase is exist. No phase is changing from one phase to another phase. It may be liquid, solid or gas. Then chemical equilibrium means definitely no chemical reaction in the system, hence it is called as the system is in thermodynamic equilibrium. Now what is thermodynamic equilibrium? The detail let we see with this video.
Thermodynamic equilibrium and quasi-static process. In this session, we will define thermodynamic equilibrium, define mechanical, chemical and thermal equilibrium, and explain the quasi-static process. What is thermodynamic equilibrium? A system is said to be in thermodynamic equilibrium if the conditions for the following three equilibrium are satisfied. 1. Mechanical equilibrium, 2. Chemical equilibrium and 3. Thermal equilibrium. When there are no unbalanced forces within the system and also between the system and surrounding, the system is said to be in mechanical equilibrium. The system is said to be in chemical equilibrium when there is no chemical reaction or transfer of matter from one part of the system to another. When the system is in mechanical and chemical equilibrium and the system is separated from the surroundings by a diathermic wall, there is no spontaneous change in any property of the system and the system is said to be in thermal equilibrium. Two systems are said to be in thermal equilibrium with each other if their temperatures are same. Thus, for the system to be in thermodynamic equilibrium, it is necessary that it should be under mechanical, chemical and thermal equilibrium. Alright, now we will see what is quasi-static process. To understand the concept, let us take a frictionless piston cylinder arrangement which contains gas at state 1 and is defined by P1, V1 and T1. The system is in thermodynamic equilibrium due to external weight W. The weight on the piston balances the upward force exerted by the gas. Now, if we remove the weight, an unbalanced force will develop between the system and the surrounding. Thus, the gas will expand and the piston will move up till it hits top. The system reaches a new equilibrium state 2 defined by P2, V2 and T2. But the intermediate states of the system are non-equilibrium states. Thus, the process is said to be non-quasi-static or irreversible process. Observe the graph where the non-quasi-static process is represented by a dotted curve. State 1 and 2 represent the initial and final state respectively. Now, in the above case, we will replace the single weight on the piston with numerous tiny pieces of weights. Let us remove the weights one by one very slowly from the top of the piston. As you can see, the gas expands slowly and it passes through a large number of thermodynamic equilibrium states. Thus, the system reaches at state 2. Here, the departure of each state of the system from thermodynamic equilibrium state is infinitesimally small. Such a process is known as quasi-static or reversible process. Observe the graph of quasi-static process, which is a locus of all the equilibrium points passed through by the system. All processes in nature are non-quasi-static. For example, expansion or compression of gas in engines, turbines, compressors, etc. Process of combustion, flow of electric current through a resistor, etc. So friends, in this session we studied the definitions of thermodynamic equilibrium, mechanical, chemical and thermal equilibrium. We also discussed the quasi-static process with the help of an experiment.
So that is regarding the quasi-static process and thermodynamic equilibrium. Now we proceed further with the new topic, that is work, heat and energy. The energy of a system is a measure of its capacity to do work. This could be the definition of energy, and the energy of a system is the sum of kinetic energy and potential energy of all particles in the system. The energy of a closed system can be changed by two aspects: work done on or by the system and heat transfer across its boundaries. So with this the energy can be transferred or can be changed. The work is transfer of energy using organized motion. It may be expansion work, electric work, etc. Or heat is the transfer of energy using thermal motion. It's a chaotic motion, and it is a random motion of molecules, that is heat, and organized motion is work. In other words, we can say if few students in the classroom are moving in any direction here to there, it is called as chaotic motion or random motion. So it creates a heat. And if all the students are moving in a single direction from one place to another place in organized motion, it is compared with the work. So heat is random motion and work is controlled and directional motion. So work is much useful as compared to heat, because we have to convert the heat into work. Directly heat cannot be used to do any kind of work. Now properties of system. Properties are any measurable characteristics of a system. For example, pressure, temperature, volume, mass and density. It can be classified as extensive property or intensive property. Two types of properties may be there, which is measurable characteristics of a system. Now first is extensive property. It is defined as are the mass dependent properties of a system, means the properties which depends on the mass. If mass varies, the property varies. That is the properties that will vary proportionately with mass of the system. For example, volume, mass, weight, enthalpy, entropy, etc. So it varies with its mass. And second is intensive property. So intensive properties are the properties that are not dependent on mass, or we can say intensive properties are independent of mass. The examples are temperature, density, specific weight, specific enthalpy, specific entropy, specific volume, etc. It means that whenever the mass gets changed, the property does not change. That is called as the intensive property. If any extensive property is divided by its mass, we would also obtain an intensive property. The examples are, if we divide weight by mass, we get specific weight. If we divide enthalpy with its mass, we get specific enthalpy. So enthalpy is extensive property, specific enthalpy is intensive property, because specific enthalpy unit is kilojoules per kilogram. So whatever is the mass, it doesn't vary. So specific enthalpy and specific entropies does not depend on mass, it's independent of mass. So this type of properties are classified as intensive properties. Now comparison of both type of properties. So this first one is mass, volume, temperature, pressure, rho. These are all can be classified like this. If we make this half mass, then volume will reduce, it will half. So these two properties, mass and volume, are extensive properties. But the temperature of this body, if this is the body, its mass is m, volume is v, temperature is T, pressure is P, and density is rho. If we cut this mass, then its temperature, pressure, and density will not change. So T, P, and rho are intensive properties. So to decide whether the property is intensive or extensive, what should we do? We should divide its total mass into half. Then think about the property, whether the property is reduced or